So imagine you are hiking through this flat, grassy valley in the middle of nowhere.
Okay, I'm picturing it.
You're surrounded by these rolling hills. They're covered in wildflowers, and there are no jagged mountain peaks looming above you anywhere.
Right, just totally pastoral.
Exactly. There are no rushing rivers nearby, and absolutely no evidence of any ancient, creeping glaciers either.
Okay.
And yet, right in front of you, just sitting squarely in the middle of this pristine meadow, is a massive, perfectly round, smooth boulder the size of a minivan.
Wow. Just totally out of place.
Completely. I mean, it looks like it was polished by a high-speed river, but the nearest body of water is like 50 miles away.
Yeah, that's a wild thing to stumble upon.
Right. So how on earth did it get there? Because geologists find rocks like this all the time, just sitting in locations where they have absolutely no geological business being.
They really do. And, the environment around that minivan-sized boulder provides zero clues as to how it arrived.
None at all, which is the puzzle we're diving into today.
Yeah, and the explanation for this phenomenon is actually, well, I think it's far more fascinating than the mystery itself.
Oh, absolutely.
Because to solve it, we really have to stop looking around the landscape and start looking down.
Right, which is the whole mission of our deep dive today. We're going to uncover these unseen subterranean rivers and hidden hydrological systems.
The ones that move these massive materials entirely in the dark.
Exactly. We're talking about rocks that have been in transit for longer than human civilization has even existed.
Yeah, moved by these huge passages that no human has ever actually entered.
That concept just completely upends how we think about the ground beneath our feet,
It really does. I mean, we walk around assuming the Earth is this static, solid foundation.
Right. But if I'm understanding the stack of sources we're digging into today, the geotechnical reports, the USGS research, all of it, the planet actually has this vast, invisible plumbing system.
A massively active plumbing system, yeah.
And it's constantly churning and, reshaping the landscape from the inside out.
And for you listening to this right now, the most crucial takeaway is that this isn't just happening in remote, exotic locations.
Like deep caves in the wilderness or something.
Right. Every single time you walk over a seemingly solid landscape, whether that's a paved city street or a manicured park or a hiking trail, there is a highly active, hidden world of sediment transport happening right below your shoes.
The ground is just a wildly dynamic environment.
It is. And today, we're going to trace the path of that invisible movement. We'll start with the slow chemical dissolution of solid rock deep underground.
Right, and then escalate to the fragile, invisible soil pipes carving out the dirt right below our infrastructure.
Exactly. And from there, we'll follow that water to a place where it seems to be flowing normally on the surface.
But it's secretly doing something completely different underneath the beds of active rivers.
Yeah. And finally, we'll plunge into the deep ocean to examine these catastrophic underwater avalanches that move at literal highway speeds.
It is quite the journey. We're going from the microscopic weathering of stone all the way to the most violent underwater events on the planet.
So to understand how that massive boulder ends up in a grassy valley, we really have to begin with our first mechanism.
Which is the dynamics of karst conduits and subterranean bedload transport.
Right. Now, when we talk about karst, we're looking at a very specific type of landscape.
The data shows karst covers roughly 15% of the Earth's ice-free land, right?
Yeah, about 15%. And we're talking about regions formed from the dissolution of soluble rocks.
Primarily carbonate rocks like limestone and dolomite.
Exactly. But let's get into the actual mechanics here because it's fascinating.
Yeah, please. Because how does a solid, impermeable block of limestone turn into a raging underground river system?
It comes down to a process called speleogenesis.
Speleogenesis.
Right. The chemistry behind cave formation is brilliantly simple, but it operates on a planetary scale. It actually starts high in the atmosphere.
Wait, cave formation starts in the sky.
It does. When rainwater falls through the sky, it absorbs carbon dioxide.
Okay.
Then it hits the ground and percolates through the topsoil, where it picks up even more carbon dioxide from decaying organic matter.
Like rotting leaves and stuff.
Yeah, and this combination creates a very weak acid called carbonic acid.
So essentially, every time it rains, the sky is dropping this very mild acid wash on the entire planet.
A mild but relentless acid wash.
Yes, that's a little terrifying to think about.
Well, when this carbonic acid seeps deep enough to meet calcium carbonate, which is the primary mineral in limestone, A chemical reaction occurs.
Okay, what kind of reaction?
The acid interacts with the calcium carbonate molecules, breaking their chemical bonds. It literally dissolves the solid rock into a liquid solution that washes away.
I have to imagine this isn't a fast process, though. Like, we aren't talking about acid burning through a metal floor in a sci-fi movie.
Oh no, far from it. The typical rate of dissolution for limestone is incredibly slow. We're talking about 0.07 millimeters per year.
0.07 millimeters. I mean, that's a fraction of the thickness of a human fingernail.
Exactly.
Oh, if I stood in a cave for my entire life, I wouldn't even notice the walls getting wider.
You wouldn't, because this process operates on deep geological time.
Right.
But over tens of thousands or millions of years, that microscopic chemical weathering does something profound.
It adds up.
It really does.
Oh.
It exploits these tiny microscopic fractures and joints in the solid rock, and it just widens those hairline cracks millennium after millennium.
And eventually, those tiny fractures become connected fissures.
Right. And those fissures become cathedral-sized underground passages.
Which is just mind-blowing.
You end up with a fully functional underground river system, which geologists call a conduit network.
And the flow rates in these newly formed conduits are what really shocked me in the research we looked at.
Oh, they are incredibly fast.
Because when we normally think of groundwater, we picture an aquifer. You imagine this giant underground sponge where water just slowly seeps through the tiny pores of sand and gravel.
Maybe moving a few feet a year, yeah.
Right. But these karst systems are a completely different animal. Geologists actually tested this, didn't they?
They did. They dropped fluorescent uranine dye into the Barton Springs segment of the Edwards Aquifer down in Texas.
Just injected bright green dye into a sinkhole to track how fast the water was moving underground.
Exactly. And the results were absolutely staggering. They measured flow rates of 0.5 to 7 miles per day.
That's up to 11.3 kilometers per day.
Which is wild. That is not a slow seepage through a sponge.
No, that is a rushing, turbulent river moving at walking speed, completely encased in solid rock.
And that incredible speed is the critical factor for why we find those out-of-place boulders.
Ah, okay. The connection to the minivan rock.
Right. Because these subterranean rivers are moving so fast, they aren't just transporting water or dissolved minerals.
They have actual physical force.
Tons of it. They possess enough kinetic energy to act as a massive underground conveyor belt for solid sediment. Geologists refer to this as the clastic load.
So they are physically pushing solid material through these caves.
From fine silts and sticky clays all the way up to rounded gravels, heavy cobbles, and yes, massive boulders.
Wow. How do the rocks even get down there in the first place, though?
They enter the underground system in a few ways. Sometimes they fall in through sinkholes that open up on the surface.
Okay, that makes sense.
Other times they're generated internally. The chemical dissolution weakens the cave ceiling so much that a massive block of limestone just detaches and collapses into the subterranean river below.
Wait, let me stop you right there and just push back on the physics of this a little bit.
Sure.
Because I understand a fast-moving surface river pushing little pebbles along a riverbed.
Right.
But if we have a cathedral-sized tunnel deep underground, and it's filled with tumbling boulders the size of cars, what does that actually sound like?
It would be terrifying.
And more importantly, if massive rocks are smashing against the walls of an underground cave, why can't we feel the ground vibrating when we walk over a karst landscape?
It's a brilliant question, and it gets to the heart of how secretive this whole process is.
Okay.
During normal, everyday flow, these caves might actually be relatively quiet.
Really?
Yeah, the water just flows over the massive rocks without moving them. But during a major storm event on the surface, the hydrology of the cave undergoes a violent transformation.
Because all that extra rainwater rushes in.
Exactly. The water table rises rapidly. Those massive subterranean conduits completely fill with water to the very roof.
So there's no airspace left.
None. The air is pushed out, and the system becomes highly pressurized.
Like a municipal water pipe right before it bursts.
Exactly like that. And when water flows through a fully pressurized pipe, it generates immense boundary shear stress along the walls and the floor.
So the water is just tearing at everything it touches.
Yeah. The velocity of the water becomes so forceful that it overcomes the inertia of those massive boulders.
It literally rips them off the cave floor.
Rips them up and starts tumbling them through the pitch blackness.
That is insane.
If you were somehow suspended in a diving bell in that cave during a flash flood, the roar of the pressurized water and the grinding, smashing impacts of massive stones colliding with each other, it would be deafening.
Just a chaotic, incredibly violent environment.
Extremely violent.
Which brings me back to my question. Why don't we feel that violence on the surface?
Because of the sheer mass of the bedrock above it, you have to remember, these conduits can be hundreds, sometimes thousands of feet underground.
Oh, wow. So there's just so much rock between us and the cave.
Right. The dampening effect of hundreds of feet of solid, dense limestone absorbs almost all of the acoustic and kinetic energy before it can propagate to the surface.
So it's this deafening roar happening in total isolated secrecy.
Exactly.
It's essentially an underground freight train made entirely of pressurized water, blasting gravel and boulders through pitch-black subway tunnels.
That's a perfect analogy, and the friction inside that freight train is beyond intense.
I bet.
As these angular blocks of rock tumble and smash through the conduits, the intense abrasion and attrition physically grind them down. They act like a giant planetary rock tumbler.
Like those little rock tumblers you'd get as a kid, but on a massive scale.
Exactly. The research notes that the particle size of these rocks is often cut in half over a distance of just 10 to 50 kilometers.
That is incredibly efficient. So they go in as these jagged blocks of collapsed ceiling, and they are quickly ground down into perfectly smooth, rounded spheres by the relentless friction.
Yeah, and eventually, this violent subterranean journey has to come to an end.
They have to come out somewhere.
Right. The pressurized water carrying these rocks reaches the end of the line. The rocks are forcefully ejected at what geologists call resurgence points or karst springs.
Ah, so the subterranean river just bursts out of the side of a mountain or bubbles up aggressively into a valley.
And it suddenly deposits these massive, perfectly rounded boulders right on the surface.
Which brings us full circle to the hiker in the valley. You are standing in a field miles from a surface river, staring at a water-polished boulder. And it didn't roll there overland.
Nope.
It didn't drop from the sky. It was spat out by a karst spring thousands of years ago after spending millennia being violently ground down in the dark.
It's incredible to think about, and what is truly vital to understand about this process is its absolute necessity for the landscape itself.
What do you mean?
Well, if you look at karst basins, which are these large geological depressions, completely enclosed by higher elevation, meaning there are no surface streams flowing out of them.
Like a giant bowl.
Right. In those bowls, this mechanical subterranean transport is literally the only way the landscape erodes and clears material.
Because there's no surface river to wash the dirt and rocks away.
Yeah.
The only exit is down.
Right. If the rocks and sediment can't be continuously flushed out through the underground plumbing system, the whole geographical region faces a crisis.
Okay, so what actually happens if that underground plumbing fails? Like, say a massive boulder gets wedged in a tight conduit and causes a log jam.
The underground passages clog with sediment, and the capacity for that subterranean river to move water drops precipitously.
So it backs up.
Exactly. When the next major rainstorm hits, all that pressurized water has nowhere to go. It backs up, blows out the sinkholes, and is forced back up to the surface.
Wow.
It can completely flood the enclosed basin, creating a massive temporary lake. It fundamentally reshapes the hydrology and ecology of the region until the water can slowly dissolve a new pathway.
That is a staggering amount of power. And it's driven entirely by water carving through solid rock over millions of years.
It really is.
But as we move to our second mechanism in this deep dive, the environment totally shifts, right?
It does. We're moving from water aggressively attacking solid limestone to water stealthily attacking something much softer, loose soil.
And while karst systems are born from water chemically dissolving solid rock, this next one is different.
Right, soil piping involves water physically carrying away loose, unconsolidated soil.
And because soil lacks the structural integrity, the tensile strength, and the sheer mass of limestone, this process is much more fragile.
Much more fragile, much faster, and frankly, much more dangerous to human life.
The geotechnical term for this is soil piping, though the literature also refers to it as internal erosion, backward erosion, or tunneling.
Yeah, those terms are all used somewhat interchangeably.
Just the phrase backward erosion sounds incredibly counterintuitive to me. Like, how does water carve a tunnel out of loose dirt without the whole thing immediately collapsing?
It's a really good question. It begins in what hydrologists call the vadose zone.
The vadose zone. Yeah.
This is the layer of soil located above the permanent water table. It's the dirt right beneath our feet that isn't fully saturated with water. It contains a mixture of air and moisture.
Right.
Now, soil isn't a perfectly uniform solid block. It is full of defects. It has macropores.
Okay, let's unpack that. What exactly constitutes a macropore? Like, I'm just picturing a hole in the dirt.
Yeah, essentially. Think of them as Tiny natural tunnels or voids. They're created by the roots of dead trees rotting away,
Oh, sure.
or burrowing insects or worms, or even just the natural expansion and contraction of the soil as it dries out and cracks.
Okay, so the soil is naturally full of all these little microtunnels.
Exactly. And when water seeps through the soil, say after a heavy rainstorm or from a leaking irrigation pipe, it doesn't just push through the dirt evenly. It finds these macropores,
It takes the path of least resistance.
always. And as the water flows through these tiny gaps, it exerts a physical drag force on the individual grains of soil.
Oh, okay.
If the flow is fast enough, it physically detaches those grains and transports them away. It washes the dirt out from the inside, leaving behind an open, invisible tube.
So it's basically a pipe made entirely of negative space, just hidden within the soil matrix.
That's a great way to describe it.
And this leads us to the specific mechanism of backward erosion piping, or BEP, which is highlighted in the engineering reports as this massive invisible hazard.
It's a huge problem.
Well, you mentioned it earlier, but I really need to understand the physics of how a tunnel grows backward.
Sure. So for backward erosion piping to occur, you need 3 very specific conditions to align perfectly.
Okay, what's the first one?
First, you need sufficient hydraulic head. That essentially means there is enough water pressure pushing through the soil to maintain a continuous, forceful flow.
Got it. Pressurized water.
Second, you need a cohesive roof. The soil sitting directly above this tiny pipe has to be sticky enough, usually containing a lot of clay or silt to hold its shape.
Like it has to act like an arch.
Exactly. It has to support the weight above it so it doesn't immediately collapse into the hole.
Okay, so we have pressurized water, and we have sticky dirt forming a roof. What's the third condition?
You need an open exit for the water to flow out of. The water and the soil it's carrying have to go somewhere.
Okay, so let me visualize this. Imagine a large earthen embankment, like a grassy levee holding back a reservoir.
Good example.
Water is slowly pushing through the dirt of the levee, and it finds a tiny exit point on the dry downstream side, maybe a gopher hole or a crack.
Right.
As the pressurized water flows out of that exit, it plucks a single grain of soil from the lip of the exit and washes it away.
Yep.
Then, because that grain is gone, the water plucks the next grain right behind it, and the next.
You got it perfectly. The pipe is literally extricating itself from the exit point, grain by grain, migrating backward toward the source of the water.
That is wild.
No.
It is digging upstream, entirely out of sight beneath the surface of the grass.
And the implications for human infrastructure are terrifying. Internal erosion, specifically this backward piping mechanism, is a leading cause of embankment dam failures worldwide.
Wait, I have to stop you there. How leading are we talking?
If you look at the historical data on dam failures,
Yeah.
roughly 50% of reported cases are caused by this invisible internal erosion.
50%.
Yes.
That is a literal coin flip on catastrophic failure caused by something you can't even see.
It's a very sobering statistic.
If half of all earthen dams fail because of backward erosion piping, why aren't we using like ground-penetrating radar or seismic sensors to constantly scan every single dam in the country? Is it just too hard to spot?
It is incredibly difficult to spot.
Way.
Well, ground-penetrating radar struggles deeply with wet, highly conductive clay soils, which is exactly what these dam cores are made of.
Oh, so the radar just doesn't work well on that material.
Right, the radar signal just gets absorbed and scattered. Furthermore, these pipes can be incredibly narrow, sometimes just a few inches wide until the very final stages of failure.
Wow.
Finding a 2-inch void inside a mile-long, 100-foot-tall earthen dam is the ultimate needle in a haystack problem.
I can imagine.
By the time the void is large enough to easily detect from the surface, the structural integrity of the dam is usually minutes away from total compromise.
That is genuinely alarming.
It is.
And the research points out it's not just giant dams out in the wilderness that we have to worry about. There's a phenomenon called SEDP, right?
Yes. Soil erosion due to defective pipes.
And this is happening right now under our city streets.
Absolutely. Urban environments are uniquely highly susceptible to soil piping. Think about what is buried under a modern city.
A ton of stuff.
You have a massive, intricate network of pressurized water mains, storm drains, and gravity-fed sewer lines.
Okay, yeah.
If a century-old sewer line develops a small hairline crack, it instantly acts as that open exit condition we talked about earlier.
Oh, so the groundwater surrounding the sewer line starts seeping into the crack, carrying the surrounding dirt with it.
Exactly. The soil pipe begins to grow backward from the cracked utility line, slowly hollowing out the earth directly beneath the asphalt road.
So it's basically like a microscopic cavity in a tooth.
That's a really good way to think about it.
It silently rots out the inside of the tooth for years. The hard enamel shell on the outside looks totally fine until one day you bite into a hard apple and the entire tooth just shatters because there was nothing left inside to support it.
That analogy captures the mechanics perfectly. The soil arch, the cohesive roof of the pipe we discussed, maintains its structural integrity for years, sometimes decades.
Wow, decades.
Yes, the system grows in total secrecy. Everything looks perfectly normal on the surface. Cars drive over it, people walk their dogs over it. But underground, that hidden cavity is getting wider and wider with every rainstorm.
Until it hits a breaking point.
Exactly. Engineers call it the critical span.
Critical span.
The moment the subterranean cavity becomes too wide for the cohesive strength of that soil roof to support the weight bearing down on it, whether that's a layer of asphalt, a passing garbage truck, or just the saturated topsoil, it fails.
And the result is a sudden catastrophic surface collapse. A sinkhole.
A sinkhole, yes.
Which makes me view my neighborhood entirely different.
I don't blame you.
I mean, with our aging urban infrastructure, century-old water mains, and changing weather patterns bringing much more intense concentrated rainfall that violently fluctuates our groundwater levels, aren't our cities essentially sitting on a ticking time bomb of unmapped growing void spaces?
It is a massive ongoing concern for civil engineers and urban planners, yes.
I bet.
The timeline of soil piping is what makes it so insidious. Because it can take decades for a pipe to widen enough to reach that critical span, the inciting event, like a cracked pipe from a minor earthquake 20 years ago, or a shift in drainage from a new housing development, might be long forgotten by the time the surface actually collapses.
So nobody even connects the two events.
Exactly. It is a completely invisible hazard, patiently waiting for gravity to win.
It's just wild to think about water acting as this stealthy thief, stealing the ground out from under our cities one microscopic grain of sand at a time.
It really reframes how you look at a pothole or a sudden depression forming in your lawn, doesn't it?
It really does. But if we take this concept of water moving invisibly through the soil, it eventually has to go somewhere.
Right.
And usually, that water finds its way into a river basin, which brings us to a place where water appears to be flowing normally, right out in the open, but is secretly harboring its own massive hidden flows.
We're moving to the beds of active rivers, mechanism 3.
Exactly. When you stand on the bank of a river and look at the water, what you see feels very intuitive and linear.
You see water moving downstream, pulled by gravity toward the ocean.
Right. But beneath that visible surface lies a concept known as the hyperhaic zone.
The hyperhaic zone.
Yes. I'm going to admit, I've spent a lot of time fishing and kayaking, and I had never heard this term before reading the research for this deep dive.
Most people haven't.
What exactly is happening down there?
The hyperhaic zone is essentially the three-dimensional subsurface interface where the surface water of the river and the hidden groundwater actively mix beneath and alongside the riverbed.
So it's not just the bottom of the river, it's what's under the bottom.
Exactly. It's the highly porous space in the gravel, sand, and cobbles located directly beneath the flowing river.
So the river is actually much deeper than the visible bottom. We only see the top layer of the water.
Much deeper and significantly wider. Because water in a river system doesn't just flow linearly downstream.
It doesn't.
No, it flows vertically down into the bed and laterally sideways into the riverbanks.
Oh, that's wild.
And this invisible movement is driven by two physical mechanisms: hydrostatic and hydrodynamic exchange.
Okay, let's unpack those terms because the physics here is really counterintuitive. Why would water choose to push down into heavy gravel when it could just flow easily over the top?
It's all about pressure. Hydrostatic exchange is driven entirely by the physical shape of the riverbed.
Okay.
Riverbeds are rarely flat. They're covered in bed forms like sand dunes, ripples, and gravel bars.
Oh, they're bumpy.
Exactly. So when the flowing water of the river hits the upstream face of a gravel bar, the physical obstruction causes the water to slow down slightly, which creates a zone of high pressure.
Okay, high pressure, pushing against the front of the gravel hill.
Right. And nature hates an imbalance of pressure.
Sure.
So that high pressure actually forces a significant portion of the river water down into the porous gravel. The water physically dives beneath the surface.
It just injects it straight into the rock.
Yep. Now, as the rest of the surface water flows over the crest of the gravel bar and down the backside, it speeds up, which creates a zone of low pressure on the downstream side of the bar.
And that low pressure creates a vacuum effect, pulling the water that dove underground back up out of the gravel and into the main channel.
You've got it. So the river is constantly undulating, diving underground, and popping back up, weaving through the sediment in a continuous three-dimensional stitching pattern.
That's just amazing. So that's hydrostatic exchange. What about hydrodynamic exchange?
Hydrodynamic exchange involves even larger pressure gradients that are driven by the overall geomorphology of the river valley.
Okay, meaning what?
These gradients force water to move laterally, pushing it deep sideways into the floodplains flanking the river.
Oh, wow. And these hidden lateral hyperhaic flow paths can be incredibly complex. In fact, they can actually flow in directions that directly contradict the surface flow.
Hold on, say that again. You're saying the water underground is moving in a different direction than the river right above it.
Absolutely. Depending on the pressure gradients and the permeability of the buried gravel layers, you can have a surface river visibly flowing due south, while the water in the hyperhaic zone 10 feet beneath the riverbank is being aggressively forced eastward, deep into the surrounding floodplain.
That is just phenomenal. To really ground how important this invisible three-dimensional plumbing is, we need to look at a fascinating piece of new research from the USGS out in Colorado and Utah.
Yes, the 2025 study.
Right. Scientists conducted this exhaustive study on the Green, Little Snake, and Yampa rivers. And they documented a phenomenon they call natural disequilibrium sediment transport.
This is a foundational concept that completely flips our conventional understanding of rivers.
Well, normally when we look at a muddy river, we assume the water and the sand floating in it are a package deal.
Right, we assume they travel together, originating from the same source upstream, moving in harmony.
But the USGS team proved that in this massive river network, the water supply and the sediment supply are completely decoupled.
Decoupled, meaning the water and the sand are showing up to the river from entirely different places at entirely different times of the year.
Precisely. In the Yampa and Green River network, the vast majority of the water comes from high up in the Rocky Mountains, driven by the massive spring snowmelt.
Okay, so you get a huge, clear rush of water in May and June.
But the sand, most of that sediment comes from lower elevation downstream tributaries, specifically the Little Snake River.
Ah.
And that sand is delivered during highly episodic, violent monsoon storm floods in the late summer.
So the river is essentially a conveyor belt that is totally out of sync with its own material supply.
Exactly.
The water gets turned on in the spring, but the heavy sand gets dumped onto the belt completely randomly during summer flash floods.
That's exactly how it operates. And because of this massive sudden influx of sand from the tributaries, the annual floods on the Yampa River generate what the researchers call elongating sand waves.
Describe an elongating sand wave for me. I'm picturing like a massive, slow-moving underwater dune.
That's a great way to visualize it. It's a massive accumulation of sand that migrates underwater down the river channel.
Okay.
And the research details the fascinating multi-year life cycle of these sand waves. It starts with what they call a year one flood.
A year one flood.
Right. This is a massive flooding event that injects a gargantuan amount of sand into the system. And as this initial sand wave moves downstream, it actually wreaks havoc on the river's complexity.
It flattens everything out.
It does. It fills in the deep, cool pools. It smooths out the rugged bottom.
Wow.
And most critically for the ecosystem, it completely buries and clogs those porous gravel beds we just talked about.
So it suffocates the hyperhaic zone.
Exactly. The fine sand fills in all the gaps between the gravel, choking off the downward and lateral flow of water.
Which has to be bad for the animals living there.
It is devastating for the local ecology because it reduces the availability of backwater habitats.
What are those?
These are the incredibly calm, warm, sheltered pools off the main channel that are absolutely critical for the survival and spawning of endangered fish, like the humpback chub.
So the big year one flood actually ruins the habitat initially. It completely clogs the underground plumbing of the river.
It does, and if the river stayed in that state, the ecosystem would collapse. But nature has a built-in multi-year cleaning mechanism.
Oh, really?
The USGS report explains that the true saviors of this ecosystem are the subsequent out-year floods.
Out-year floods.
These are the floods that happen in year 2, year 3, and year 4 after the initial massive sand dump.
Okay, but what if these out-year floods are smaller in magnitude than the year one flood? Do they still help?
Even if they are smaller. Because the massive sand wave is already in the channel, these subsequent floods act as a scouring force.
I see.
Over multiple seasons, they slowly erode the back end of that massive sand wave. They physically migrate the sand further downstream,
Oh,
and as the sand is moved out, it scours and flushes the gravel beds clean.
they unclog the drain.
Yes, and by flushing the fine sand out of the heavy gravel, they restore the porosity of the riverbed.
So the deep, oxygen-rich hyperhaic flow paths are reestablished.
Exactly. The backwater habitats deepen again, and the endangered fish have their vital spawning grounds restored.
That is amazing. It's this delicate, incredibly complex, multi-year dance of sediment moving invisibly along the river bottom,
It truly is.
which immediately makes me think about human infrastructure,
Uh-oh.
right? Because if this highly delicate balance of out-year floods over multiple seasons is required to manage the sand and clean the gravel, how does human intervention mess up this invisible cleaning system?
It messes it up significantly.
The research specifically mentions the massive Flaming Gorge Dam on the Green River, doesn't it?
Yes, it does. Human intervention, particularly large dams, profoundly and often catastrophically alters this disequilibrium system.
How so?
Well, a dam like Flaming Gorge exists to regulate water flow. It changes the natural timing and the volume of the water supply.
Right.
It holds back the spring melt and releases it slowly over the year, effectively flattening out the natural flood peaks.
So it basically kills the velocity of the river.
Exactly. And if a dam prevents those critical out-year floods from reaching the necessary velocity to move heavy sand, the cleaning mechanism breaks down.
The sand wave never gets flushed out.
Right. The gravel beds stay permanently clogged, the hyperhaic zone suffocates, and the endangered fish populations inevitably crash.
That's tragic.
The research makes it definitively clear. The health of these river ecosystems is dictated not just by how much water is flowing on the surface, but by the complex longitudinal patterns of bed sand migrating invisibly along the bottom.
It's all about managing the hidden sand.
It is.
And what I found so beautiful in the research is that the ecological magic of this hidden system extends way beyond the fish in the water.
Oh, yeah, the plant life.
The data shows how these lateral hyperhaic flows, the water being pushed sideways into the riverbanks by those pressure gradients, literally keep the surrounding desert alive.
It is one of the most elegant connections in the entire study of hydrology.
I mean, in these harsh dryland environments, the lateral movement of water through the hyperhaic zone does something extraordinary. It effectively cools the floodplain soils at root depth.
Right.
Advective cooling, meaning the physical movement of the cool mountain river water migrating underground acts like a subterranean air conditioner for the soil.
That is exactly what it is. During the peak of summer, when the desert sun is relentlessly baking the surface soil and air temperatures are soaring, this hidden, cool water is actively circulating 10 feet underground.
That's incredible.
This intense temperature buffering is what keeps the iconic Fremont cottonwood forests alive in an otherwise lethal desert environment.
So without that invisible lateral flow pushing sideways into the dirt, the roots would bake and the forests would perish.
They wouldn't survive a single intense summer. The entire riparian corridor relies on water they can't even see.
That is just phenomenal. An invisible underground air conditioning system powering an entire forest.
Nature is incredibly resourceful.
It fundamentally changes how you look at a river.
Hmm.
It's not just a two-dimensional line of blue water drawn on a map. It is the pulsing heart of a massive three-dimensional underground circulatory system.
It truly is. But as vast and complex as that circulatory system is on the continents, it pales in comparison to what happens when that sediment finally reaches the end of the river and spills into the ocean.
Right. We are now going to scale up to the fourth and final mechanism.
The most extreme form of invisible sediment transport on the planet.
One that takes place entirely underwater, in total darkness, on a scale that dwarfs everything we've talked about so far.
Yes.
We are leaving the continents behind and heading to the abyssal depths. Mechanism 4. Deep ocean turbidity currents.
Even just the phrase turbidity current sounds ominous.
It really does. What exactly is it?
Well, the sheer scale of them is almost incomprehensible. A turbidity current is essentially a colossal underwater avalanche.
Wow.
It is a massive flow of sediment and water that mixes together to become significantly denser than the surrounding clear ocean water.
Okay, so it's heavy.
Very heavy. Because it is so heavy, gravity takes hold, allowing this dense cloud to plunge violently down the continental slopes and out onto the flat abyssal plain of the deep ocean.
And because this phenomenon happens miles underwater, in absolute darkness, under crushing pressure, Scientists literally couldn't measure them or even prove they existed for the longest time, right?
Right, it was entirely theoretical.
Until a specific day in history changed everything.
November 18th, 1929.
The Grand Banks earthquake.
Yes. The 1929 Grand Banks event is legendary in the field of marine geology. It provided the ultimate undeniable proof of these hidden forces.
Tell me about it.
The epicenter of the earthquake was located south of Newfoundland, Canada, right on the edge of the continental slope. A magnitude 7.2 earthquake violently shook the seafloor.
A 7.2 is massive.
Yeah.
But reading through the historical seismology papers, the earthquake itself, while huge, wasn't the main event.
No.
It was what the violent shaking triggered.
Right. Decades of glacial sediment, mud, sand, and gravel carried off the continent by ancient ice and rivers had piled up precariously on the edge of the continental shelf.
Like a snow cornice waiting to snap.
Exactly. And when the 7.2 earthquake hit, the intense seismic waves caused a phenomenon known as soil liquefaction.
We really need to explain liquefaction because it sounds like magic.
Yeah.
How does solid dirt suddenly become liquid?
It has to do with the water trapped in the microscopic spaces between the grains of sand and mud.
Okay.
Under normal conditions, the grains of sediment rest on top of each other, providing structural friction. But when intense seismic shaking occurs, it rapidly compresses the sediment.
Right.
The water trapped between the grains has nowhere to go, so the water pressure skyrockets.
The water pressure pushes back against the dirt.
Exactly. The pressure becomes so intense that it literally pushes the individual grains of sand apart.
Oh, wow.
They lose contact with each other. The friction drops to zero.
So they're just floating.
In an instant, a solid mountain of dirt loses all its structural integrity and behaves exactly like a fluid.
That is terrifying. And the volume of material that liquefied during this specific earthquake is just staggering.
It is hard to wrap your head around.
The estimates suggest that between 100 and 200 cubic kilometers of glacial sediment slumped and gave way.
Let's put that number into a perspective we can actually visualize. 100 cubic kilometers is the equivalent of about 24 cubic miles of solid earth.
24 cubic miles.
Imagine a solid block of mud and sand that is 1 mile wide, 1 mile high, and 24 miles long.
That is just a mountain range.
Now imagine that entire mass suddenly turning to liquid in a matter of seconds and plunging off an underwater cliff.
It is genuinely unfathomable. This liquefied mass transformed into a turbidity current that the historical data indicates was up to 300 meters thick.
300 meters thick.
That is a 1,000-foot-high wall of dense mud cascading blindly into the abyss.
It is apocalyptic.
And the physical displacement of that much water was catastrophic for the surface. It generated a massive tsunami that swept over the Burin Peninsula in Newfoundland, tragically killing 28 people and wiping out coastal communities.
The surface impact was devastating and immediate.
Right.
But what was happening deep underwater, entirely out of sight, remained a complete mystery to the people on land at the time.
Because they couldn't see it.
This massive turbidity current surged down the Laurentian fan, heading toward the flat, some abyssal plain. And it was moving at astonishing, seemingly impossible speeds.
How fast?
Modern estimates put the velocity between 60 to 100 kilometers per hour.
Underwater?
Underwater. Some highly conservative models suggest peak speeds might have even reached 130 kilometers per hour down the steepest parts of the slope.
But here is the crux of the mystery. How do we actually know that?
Right.
It was 1929. No one was down there with a submarine and a radar gun. There were no deep-sea sensors.
None.
This is where the historical narrative turns into an incredible scientific detective thriller.
Because this invisible avalanche left a very specific, perfectly timed trail of destruction.
Exactly. In 1929, long before satellites, the seafloor of the North Atlantic was crisscrossed with a vast network of transatlantic telegraph cables.
Yeah, these thick copper core cables were the absolute vital lifeline of global communication between North America and Europe.
And when the earthquake initially struck, 6 cables located in the immediate epicenter zone snapped instantly due to the violent ground shaking in the initial slump.
Right, the telegraph operators in New York and London just saw those lines go dead at the exact moment of the quake. That makes sense.
But then a very strange, terrifying sequence began to unfold over the rest of the day.
Over the next 13 hours and 17 minutes, the remaining telegraph cables, which were located further and further south, descending into the deep ocean basin, began to snap one by one in sequence.
Wow.
In total, 12 thick, armored cables were severed.
The telegraph companies were completely baffled. They had operators sitting at desks, knowing exactly when each cable failed because the transmission line just vanished.
But they had absolutely no idea why a cable located hundreds of miles away from the initial earthquake epicenter would suddenly, violently snap 13 hours after the ground stopped shaking.
It was an unsolved mystery for over 2 decades.
It wasn't until 23 years later, in 1952, that researchers Bruce Heezen and Maurice Ewing finally put the pieces together.
What did they find?
They were reviewing the old telegraph company logs, and they realized that the earthquake hadn't just shaken the ground, it had triggered a massive turbidity current.
Okay.
And this dense wall of moving mud was what sequentially snapped the cables as it raced southward.
And this is the genius part. They used those corporate telegraph records, the exact down-to-the-minute timestamps of when each communication line went dead, to mathematically calculate the velocity of the flow.
It was a brilliant application of basic physics to solve a massive geological mystery.
So elegant.
They mapped out the precise locations of the broken cables on the seafloor. They knew the exact distance between cable A and cable B, and thanks to the telegraph logs, they knew the exact time delay between when cable A snapped and when cable B snapped.
Distance divided by time equals speed.
Exactly. That is exactly how they proved to the scientific community that this underwater mudslide was moving at highway speeds across the ocean floor.
But Heezen and Ewing didn't just stop with a math equation on a chalkboard. They needed physical, undeniable proof that sediment had actually moved that far.
They did, so they organized an expedition, sailed out to the Grand Banks, and conducted seismic refraction surveys.
And crucially, they dropped hollow tubes deep into the ocean to take physical sediment cores from the abyssal plain.
And what they found in those cores fundamentally rewrote marine geology.
What was it?
Well, they looked at the sediment resting on the deep, flat abyssal plain, hundreds of miles out from the continental slope.
Okay.
In normal, undisturbed areas of the deep ocean, they found exactly what you would expect to find, what they described as normal, blue, silty mud.
Just fine dust.
Right. This is the microscopic, fine dust and biological matter that slowly, gently settles out of the water column over millions of years.
But when they took cores directly in the projected path of the turbidity current,
They found heavy gravels and coarse continental sands sitting directly on top of those older, fine, silty muds.
heavy gravel, sitting on the deep ocean floor up to 1,000 kilometers away from the underwater canyon where it originated.
Finding large gravel 1,000 kilometers out on the completely flat abyssal plain was the smoking gun.
It had to be.
It was absolute, undeniable proof of the staggering force, density, and sustained speed of that current. Water gently moving at the bottom of the ocean cannot move gravel.
Only a violent, heavy flow can physically carry heavy stones that far across the ocean floor.
Exactly.
Okay, I have to stop and push back on the physics here, because this defies common sense about how water behaves.
How so?
If you try to run as fast as you can in a swimming pool, the friction and resistance of the water stops you almost immediately. Water is incredibly dense.
True.
How does a massive wave of mud plowing through the crushing pressure of the deep ocean not just immediately slow down due to friction and stop? How does it travel 1,000 kilometers?
It's a highly intuitive question. The answer lies in a fascinating physical phenomenon known as autosuspension.
Autosuspension.
The researchers studying the dynamics of these flows realized that a turbidity current isn't just a uniform, cloudy mixture of muddy water. It has a highly specific internal structure.
Okay, break that down for me.
At the very front, or the head of the flow, and running aggressively along the bottom, is a highly dense near-bed layer.
How dense are we talking? Like a thick soup?
Denser. The research indicates this basal layer can reach a 10 to 30% concentration of solid sediment.
So it is practically liquid rock.
Yes. This dense layer is incredibly heavy, and gravity pulls it down the slope with immense, unrelenting force.
Wow.
Now, because this bottom layer is so highly concentrated and heavy, it doesn't easily mix with the clear, lighter ocean water above it.
Ah, it creates a boundary layer.
Exactly. This boundary layer drastically reduces the fluid drag that would normally slow it down.
That makes so much sense.
But the real magic is the turbulence. Because this heavy layer is moving so fast over the seafloor, the intense turbulence physically scours and stirs up even more sediment from the bottom,
Just ripping up the seafloor as it goes.
continuously feeding fresh material up into the flow. The current is literally consuming the seafloor to maintain its own density. It generates its own momentum.
It's an engine that fuels itself.
Yes. This self-sustaining cycle of autosuspension is what allows turbidity currents to travel vast distances, like those 1,000 kilometers on incredibly low gradients.
Even when it flattens out.
Once the current reaches the abyssal plain, it is moving across slopes of just 0.05 degrees.
0.05 degrees is virtually flat. You wouldn't even be able to tell you were standing on a hill.
It is essentially flat, yet the current maintains its staggering speed because it is so heavy and so turbulent that it just keeps gliding and scouring its way forward until it finally runs out of material to consume.
That is deeply unsettling. A nearly flat ocean floor in pitch darkness under miles of water, and yet a 100-foot-high avalanche of mud is tearing across it at 100 kilometers an hour.
It's terrifying, honestly.
Which leads me to an obvious modern concern. Could something like this happen today?
Oh, absolutely.
And if it did, wouldn't it instantly wipe out the modern internet? I mean, we don't rely on copper telegraph cables anymore, but our entire global data network is entirely dependent on thin, undersea fiber optic cables resting on that same seafloor.
It is a very real, incredibly present threat. Submarine landslides and the resulting turbidity currents are still actively heavily studied by geologists precisely because they threaten our critical modern infrastructure.
I can't even imagine the fallout.
If a major earthquake triggers a slope failure near a major fiber optic corridor, say off the coast of Japan or California, we could easily see a catastrophic sequence of cable breaks, just like the 1929 Grand Banks event.
It could instantly sever massive amounts of beta connections between continents.
The geological mechanics of the ocean floor haven't changed one bit in the last century. Only our immense reliance on what is resting on it has changed.
The invisible forces are still down there, loaded, and waiting for the right trigger.
Absolutely. And if we take a step back and bring all of this together, what we are really looking at across all four of these distinct mechanisms is a continuous planetary scale operation.
Right.
Whether it is the slow, relentless chemistry of weak carbonic acid dissolving solid limestone molecule by molecule over millennia,
Or pressurized water exploiting microscopic macropores in the dirt to slowly backward pipe a massive hidden void under a busy city street.
or the complex lateral hyperhaic pressure gradients secretly flushing fine sand through heavy gravel beds to keep desert cottonwood forests alive in the sweltering heat.
Or a 300-meter-thick underwater avalanche triggered by an earthquake, snapping steel cables at 100 kilometers per hour in the absolute abyss.
The underlying truth governing all of it is exactly the same. The Earth is constantly, actively moving vast, incomprehensible amounts of its own mass entirely out of human sight.
It really changes your perspective.
The surface we stand on, build our cities on, and hike across is just a thin, temporary crust resting over a remarkably dynamic, violent plumbing system.
Which brings us right back to our opening hook. That perfectly rounded, utterly out-of-place minivan-sized rock sitting in a pristine, grassy valley.
It's not a mystery at all.
No, it is simply the visible endpoint of a violent, dark, and highly efficient journey. A journey that takes place on timescales and in environments that are practically impossible for us to observe directly.
Exactly.
That boulder survived the underground freight train. It was tumbled, polished, and spat out by a planet that is constantly remodeling itself from the inside.
It certainly did. And if we connect this localized understanding of Earth's plumbing to the grander cosmic picture, it leaves us with a truly mind-expanding question to ponder.
Oh, I like where this is going.
We now understand that these massive invisible subterranean and subaquatic conveyor belts are actively reshaping Earth in total darkness.
Right.
So what hidden hydrological or clastic networks might be silently churning right now beneath the dusty alien surface of Mars?
Oh, wow.
Or deep under the miles-thick, cracked ice sheets of Jupiter's moon Europa? If fluid, rock, and gravity exist together in the dark anywhere in the universe, the unseen rivers are almost certainly flowing.
I genuinely have chills. That is an incredible thought to end on, expanding our invisible plumbing system to the rest of the solar system.
It's a big universe out there.
Thank you to everyone for joining us on this deep dive into the hidden churning mechanics of the planet. I guarantee you're going to look at the solid ground beneath your feet, the potholes in your street, and the water flowing in your local river a little differently today.
I know I do.
Keep wondering, keep looking down, and we'll catch you on the next deep dive.